intended for tank inspection, so that it could go in and actually inspect the inside of a tank without having to empty the tank. So that if the tank had fluid or liquid in it, it could actually be dropped in and inspect for cracks, leaks, that type of thing.
Houdini was created for cleaning radioactive sludge out of nuclear waste chambers. Like its namesake, Houdini can crawl into places other robots can't.
For robots that will work inside tanks, inside pipes, inside mines and caves, there are two approaches. One is to forcefully make openings large enough to enter. The other is to collapse, become small enough to go through existing openings.
This particular robot folds like a parallelogram, so it can go down a 22-inch diameter opening. And that's typical of the kind of openings that were left in a lot of these nuclear waste tanks. So as the bulldozer folds, it goes down in the tank, opens back up, and then it can move waste around in the tank to the clean out sumps and so forth.
Today, a new generation of the Houdini robot, called Pioneer, is being developed and tested at Red Zone for use at the Chernobyl nuclear accident in the Ukraine. The radiation levels at Chernobyl were so massive that over 30 of the first humans to investigate it died within weeks or months. Researchers learned quickly that if they weren't careful, extreme radiation could spell death for robots too. By melting electronic wiring, fogging camera lenses, and destroying rubber treads. Most field robots rely on wheels and tracks to navigate through perilous terrain. But many jobs require another, more complex system of locomotion.
Perhaps a third of this world, and maybe much more of other planets, is inaccessible to the traditional locomotors like wheel tracks. Legs, as manifested in nature, show incredible ability to climb and maneuver, to scale near vertical walls. And this motion can theoretically be done with efficiency beyond that achievable with wheels and tracks.
Early experiments with legged movement, like General Electric's walking truck, known as the Elephant, found few uses and were incredibly expensive. In the early 1980s, Ivan Sutherland built his walker. The position of the 6 legs were controlled microprocessors, while an 18-horsepower engine propelled the robot at about 2 miles per hour. Sutherland's design gathered valuable knowledge about balance and coordination. Although the attempt was interesting, it was not very practical. The answer to many of the problems facing walking robots came from California's Odetics Corporation and their Odex-1 Functionoid. It could navigate relatively flat surfaces with ease. It also had amazing balance, climbing ability, and strength, able to lift several tons using its entire body, or up to 450 pounds with a single leg. But independent thought and outdoor navigation still eluded even this impressive robot. Ambler was created at Carnegie Mellon to be fully autonomous and take on tough terrain like large boulders and deep crevices. Unlike animals or insects, Ambler could move any of its 6 legs independently. The robot's vision and reasoning systems allowed it to plan leg placements up to 1,000 moves ahead, as if playing a masterful game of chess.
The first couple times we moved it, it was pretty scary. It's almost like a building next to you is getting ready to shift. Almost all of these things, when you first start them up, you don't know what they're going to do. So you sort of put them in a condition where they're not going to hurt anybody, and you stand back.
But this much thought required a massive superstructure weighing thousands of pounds.
Ambler was self-contained, self-reliant with everything on board. Once the sensing came on board, once the computers came on board, there was a need for power. That increased the mass, that increased the scale, and this was a problem that spiraled, feeding itself, and the scale of Ambler is a result.
Ambler had been intended to explore Mars, but its monstrous size made that trip impossible. Instead, Red Whittaker's team had to find new, dangerous territory on Earth for Ambler's descendants. The scientists chose the Mount Erebus volcano in Antarctica. The robot to explore this uncharted hellhole was an 8-legged walker known as Dante. The robot went through rigorous testing on the slag heap of an abandoned Pittsburgh steel mill before making the 13,000-mile trip to the White Continent.
We deployed Dante onto the volcano in thousands of little pieces and parts with 250,000 lines of fresh software, new sensors, new physical form. In tents at 10,000 feet, we assembled it piece by piece, downloaded software, brought it to life. I was amazed this thing walked.
In the end, it was ice rather than fire that killed Dante. Wiring and circuitry intended to withstand the extreme heat of an active volcano was unable to survive the severe cold at the top of the mountain, and Dante failed after only 3 steps. The makers of Dante went back to the drawing board and redesigned their creation. New leg configurations, joint placements, and metals made Dante 2's legs 3 times as strong as its predecessor. Dante 2 was sent into Mount Spur, an Alaskan volcano. Step by step, it negotiated loose terrain and withstood a barrage of falling rocks as it made its unprecedented descent. Dante's sensors allowed researchers to take seismic readings, view video images, and even smell the chemical content of the air, all from their command post in Anchorage, over 200 miles away. Eventually, the extreme terrain and high winds combined to tip over Dante 2, and the robot had to be airlifted to safety. Red Whittaker and his field robots team have helped build an industry for robots that step in when our own technology backfires. They've gone into nuclear reactors and noxious volcanoes. But other scientists are dealing with a subject even more daunting: rush hour traffic. Like an infant learning to walk, robots had taken their first awkward steps. But like a teenager learning to drive, true freedom would only come once robots could travel great distances on their own. In 1979, Hans Moravec brought the knowledge from his Stanford cart to Pittsburgh and joined forces with a team from Carnegie Mellon University to create mobile robots. Carnegie Mellon researchers had been working on their own cart called the Intelligent Mobile Platform, or IMP. This hallway navigator borrowed autofocus sonar technology from Polaroid cameras to map its world. It scanned its environment as a lighthouse would, but sonar proved to have severe limitations.
It can't see very far away. It has a problem if you have a smooth surface, the sonar just hits the smooth surface and bounces and never comes back. And so you may think that there's nothing there when in fact there's a nice smooth wall.
Moravec's next project with the Carnegie Mellon team, called Uranus, used specially designed wheels to overcome some troublesome technical issues.
Uranus exhibits that unique ability to move instantaneously in all directions, not just like we drive a car, but also to move laterally, spin on a dime, or to pirouette so it could turn while moving. And we couldn't solve the parallel